And last week I was on international travel for a conference. So we have two guest lectures. One is on quantum computing, one is on the hardware architecture for machine learning. So if you miss those lectures, you are encouraged to watch the YouTube video to record it. So TA already posted that online. And today we are going to have our discussions deep into the physics of the semiconductors, because we have talked about the silicon technology used for today's integrated circuits and all the computer systems. So today we are going to look at the properties of the silicon material, because that is the foundation for all the chips we are building today. And we will first look at from a bound model point of view. And I will talk about in more details what is a bound. And then next lecture we are going to view this from the band model point of view. Alright, so this is the textbook and the chapters. So as I announced in the email, the link to download this PDF is temporarily unavailable. So I asked the permission from the Professor Chiming from UC Berkeley, and he agreed that I can upload the PDFs to our Canvas system. So you can also download from Canvas system about the PDFs of the textbook. And also Professor Asif Khan's recorded lecture from the past semesters available here. Alright, you have seen this before. So this is Intel's processor at 14 nanometer low, introduced 2014. And you have seen this cross-sectional view of the chip. So if you cut the chip and look at the side, from the side, you will see many layers of the interconnect. And we talk about the interconnect is made of metal. And then we spend one lecture on the metal properties, and we talk about the copper. And we look at the mobility of the copper and the electron density of the copper. So eventually you can get the resistivity of the copper. And we prefer copper as the metal interconnect. So you see many layers of the metal interconnect. And down to the bottom, this is the transistor. That is the building block for all the digital circuits. And in particular, this is a MOSFET transistor, MOS, FET, metal oxide semiconductor field effect transistor. And then the substrate is a silicon. So all the transistor is built on top of the silicon substrate. And today we are going to look into the silicon properties in more details. So here is a zoom in of this transistor here. So let's further take a look about this transistor structure. So you see here, this is called a FinFET technology. So this is like a fin. So if you think it's a fish, so this is like the fin if you look into the plane. So then this is made of silicon, as I said. So the substrate here is all silicon. Of course, here this is silicon S, and then this part is oxide, and this part is metal. So it's a MOS, metal oxide semiconductor field effect transistor. And today we are going to look at the silicon in more details. So this is a zoom in of this structure. And in this silicon fin area, this is at the atomic scale. This is under a very high resolution transmission electron microscopy here. So you can really see the silicon atoms here. So if you, maybe the resolution on the screen is not that good, but if you look at the lecture slides on your computer, then you will see the individual atoms here. So those are the silicon atoms. And if you look at the scale of this structure, so here is a scale bar. It says 5 nanometer. So here the fin width is about like 7 nanometer to 8 nanometer also. So it's pretty small. And under such scale, you can really see the individual atoms, silicon atoms. Question.
So why does it take the thin shape?
What is a fin shape?
But why does it take on the shape of a fin?
Why do we make a fin? That's your question?
Yes, sir.
Okay, that's what we are going to discuss at the very end of the semester. So this is some advanced technology. In the MOSFET structure, we are going to learn. For most part of the semester, it's a planar structure. It's not like this. This is for technology below 22 nanometer. So industry introduced the FinFET structure. And we are going to have that covered in the very end of the semester for the advanced topics. And we will discuss why we need the fin structure there. But normally it's a like planar structure. It's like a piece of silicon, flat, not like this shape. So we'll talk about this in more details later. Yeah. So here you see the individual atoms, and we are going to discuss the silicon properties, because this is really atomic scale. In total, you may only have like 50 atoms or 60 atoms around here. Okay, so for the silicon, if you look at the periodic table, so can you find the silicon there? Where is it? Somewhere in that column. So it's here, silicon, and the atomic number is 14. It's the 14th element, and it's in that column. So that column is one group called fourth group. Right? So it's fourth group. This is because the most outside, the outmost shell has 4 electrons in that group. So it's group number 4. And along that group, you have carbon, silicon, germanium. So this is typically semiconductor, because you know, towards the left-hand side here, most of the materials are metal, and towards the right-hand side here, most of them are like inert elements, or let's say insulating. So then this is somewhere between. That's why it's semiconductor. So let's look at the silicon's crystal structure. And you have seen this similar kind of crystal structure for copper in the last lecture. And here is the silicon. It's different if you look at the crystal structure here. So each ball here is a silicon atom. And this is the unit cell of the silicon crystal structure. So in the three-dimensional space, you're going to repeat this kind of unit cell into three-dimensional space. And then the distance here for this, let's say, one side of the unit cell is about 5.43 angstrom. And you know, angstrom is 0.1 nanometer. So this is the 0.543 nanometer. And silicon is number 14. And this is the orbital information for the silicon. And the most outside shell is a 3s orbital and 3p orbital. And 3s carry 2 electrons, and 3p carry 2 electrons. So the shell has 4 electrons, 3s and 3p. Each contribute 2 electrons. So in total you have 4 electrons. That's also why silicon is in the group number 4 in the periodic table, because the most outside shell has 4 electrons. So those 4 electrons actually will form the covalent bond with the neighboring atom. So here if you look at one atom, one silicon atom here, it will have 4 electrons. Around it. And then those 4 electrons will for a bond with a neighboring silicon atom. Because you know one bond is 2 electrons. So for example, this atom will contribute another electron here. So those 2 electrons will form a covalent bond. So you can see that around one silicon atom, there will be 4 bonds. And each bond is 2 electrons. Of course, a single silicon atom only contributes half of the bond. So in total, you have those 80 electrons around one silicon atom, but 4 of them are from itself, and the other 4 are from the neighboring cells. So any questions here for this crystal structure? You can compare this with copper, it's different. Okay, so then here we have some terminologies about the orientation of the silicon wafer. So because the silicon, as we showed in the previous slide, actually is a 3-dimensional structure, right? So you are going to repeat that unit cell into 3-dimensional space. But the silicon wafer, as you see in the previous video I showed, you are going to have that pizza, right? You are going to cut that cylinder into a 2-dimensional wafer. So then the question is, how do you cut that crystal structure into a 2-dimensional wafer like your pizza? So what is the orientation of this wafer? So then there are different possible ways to cut the 3-dimensional crystal structure into this 2-dimensional wafer. So here, if you look at the crystal structure here, we skip the atoms, but here we basically draw that unit cell. So here you have this unit cell, it's a cube. And then we show this cube. Of course, you have x, y, z, 3 axes for the cube. And then we are going to cut this crystal structure into a 2-dimensional wafer. So then here the shaded side is the surface of the wafer. For example, this wafer is to cut the crystal structure using this surface, this shaded surface. You cut the 3-dimensional. If you have a knife, then you cut through that slice. Of course, you can use knife to cut that. So then this is the one way to make the wafer. And we are going to learn the orientation using the index there, like 100 for this cut. So the 100 is because here you look at the intersection of this shaded surface. The intersection with x-axis is, let's say, normalized to 1. And this surface is in parallel with y and z plane. So it will never intersect with y and z plane. So the index x, y, z here, the first one is 1 because it intersects with the x-axis, let's say at the unit length 1. And then it will never intersect with the y and z, so we give 0 as the index here. So this orientation is called 100 orientation. So essentially, we are talking about the surface, and then the orientation is perpendicular to the surface. So this is 100 cut. And we name this wafer as 100 wafer. So we are pointing out from the plane, and we call it 100. Of course, you have different ways to cut the crystal. Then the second figure shows 0, 1, 1 cut. So again, this is x, y, z. So 0, 1, 1. That means what? The first one is x. If it's 0, that means that plane will never intersect with the x plane. So it's in parallel with x. But it intersects with y and z at 1, 1 location. So you look at this surface. So for the y and z, so this intersect at z equals to 1, and also it intersects with y at 1. But that plane never intersect with the x axis. So that's why x is 0.
If you cut such that you only intersected with the y plane, would you denote that as 0, 1, 0? Like,
0, 1, 0.
would that be a cut that would be perpendicular to the
Yeah,
0,
yeah.
0 cut?
Yes, you can do that. Yes, yes. This is just an example in the second figure. Yeah. So for the third one, this is another possible cut. So if you cut this way, right, then it will intersect with x, y, z at 1, 1, 1. So this is called 1, 1, 1, 1 cut. So there are different ways to cut the wafer. Because it's a three-dimensional crystal, you need to make a two-dimensional wafer. So you have different ways to cut. But this 1, 0, 0 is a common cut for the crystal, silicon crystal. So what matters later, as you will tell, is the mobility of the electron will be different if the cut is different. Essentially, you are going to build your transistor on this wafer, so electron is to travel through some direction. So because the cut is different, the electron may see different kind of crystal structure, so the scattering will be different. You may see more like the atoms along the travel direction of the electron. Then you may have different velocity or mobility of your electron. So the way how you cut will affect how fast the electron travel along the surface of the silicon. So this is what we are going to discuss later. But here I just want to introduce the possible way to cut the wafer. Any questions? Okay, so here is some image under the scanning tunneling microscope, which is a very fancy technique to look at the individual atoms. So this one even has higher resolution than the transmission electron microscope. So here what you see in this image is the individual atoms, and here it's viewed at some angle. So you do see this crystal structure, and this it says it's looking into 0, 1, 1 direction. So it's a cut of this, the second figure here. The wafer is this kind of wafer, and you are looking into this wafer from possibly this view. You are looking at here. So this is how you look into the wafer from this scanning tunneling microscope. You do see some bigger atoms, right? So that probably is your, let's say, most outside plane, because you look into the silicon, it has multiple silicons farther from you, right? So you look into the three-dimensional structure. So you have the repetitive structure, and then the biggest one is the closest plane to you, to your eye. Okay, so this is just an example. But let's simplify the view of this. So in many of our analysis later, we don't need to think about this three-dimensional picture because it's very complicated. In order to, let's say, simplify the physical picture, so let's just assume this two-dimensional bump structure. of course, it's a three-dimensional structure, but if we want to make it simple, let's assume that it's like a two-dimensional array like this. So here we have individual silicon atom, and then as we discussed, one atom will have 4 labels. Of course, this is a two-dimensional view. It's not correct. As we just showed earlier, it's really a three-dimensional bonding structure with different angles. But let's just assume it's a two-dimensional thing here, for sake of the simplicity. And then here we said we have 4 nearest neighbor to form 4 bonds, and each silicon is going to contribute 4 electrons here. Of course, the neighboring cell will contribute additional electrons here. So you form those 4 bonds with 8 electrons. And here is a load at temperature 0 Kelvin, which is absolute 0 temperature, which is negative 273 Celsius here, which is very, very cold. Actually, you cannot reach that temperature from the physics. It's a theoretical lower limit for everything. So at this absolute 0 temperature, all the bonds are satisfied. That means the silicon structure has those bonds, and all electrons are bonded with each other. If the electrons are bonded with each other, that means the electrons cannot move under the external electric field. Then the silicon looks like an insulator. Because all the electrons are local, they are bonded, they cannot move. So then there's no free carrier, no free electron. No free electron, no current flow, so then it's like insulator. This is only true at T equals to 0 Kelvin. That means it will not exist in reality, because in reality you cannot reach that temperature. So what happens in reality, which means some finite temperature, T larger than 0 Kelvin? So, the temperature really means energy, right? Temperature is a measure of thermal energy. So then if you have higher temperature than 0 Kelvin, that means the electrons may have some kinetic energy, thermal energy. So that means they can somehow break the bond, break the covalent bond. There are some possibilities. So let's say if the electron here, this bond, broken, then the electrons will become free electron. Free electron means they can move under external electric field. If you have electric field, then the electrons can move. So if the bond is broken due to some thermal energy, then if you have the external electric field, then the electrons will move, of course, opposite to the electric field direction. And here we are going to introduce one important concept. Because you have free electron move, so it will leave a vacancy of the electron here. So let's say if the electron belongs to this silicon, but if it moves from here to here due to the external electric field, so what is left here is a vacancy of the electron. And we are going to call this vacancy of electron as a hole. this is called a hole.